Right, so basically three parts of my talk: the work I did for my PhD, the work I will be doing for my postdoc, and then why I'm here. Okay, I'll kind of try to go quickly through these background slides because we all know this. So looking at observations of end of summer sea ice extent and area, models are doing a better job of predicting the end of summer sea ice extent, but there is still a widespread in the predictions or in these models, and there's different kinds of theories for why there's still a large spread, and kind of getting into some of that really quickly. Some subgrid scale processes like melt ponds have to be parameterized. So looking at melt ponds on first year ice on the left, multi-year ice on the right. In the summer, melt ponds form as the snow melts, and they're on the scale of tens to hundreds of meters in width, so not resolved by these larger models. So we have to look at how we can parameterize these and study these for models. And they're different depending on the ice on which they form. So on first year ice, they can spread easily across the surface because there's not a lot of surface topography, and the snow distribution is pretty level. Whereas on multi-year ice, there's more of these undulating features, ridging, deformation events. And so the ponds are kind of confined to these smaller areas. Also, the melt pond albedo and color is dependent on the depth of the melt pond and also the thickness of the underlying ice. So it looks different depending on which ice type it's forming on. And as we know, the Arctic's kind of transitioning from this predominantly multi-year ice regime to more first-year ice. So thinking about how melt ponds are changing as we kind of see a change in the Arctic ice cover. And when you think about how to incorporate these in models, it's important to include melt ponds in models because they have enhance this shortwave absorption and contribute to these positive feedbacks. So in this particular study, looking at the impact of ponds on these simulations, looking between the dashed line and the dotted line, that's where you'll see the impact of melt ponds. So on the left-hand side, you can see the sea ice area decreasing when you start including melt ponds, and then sea ice thickness also decreasing and becoming more realistic. Right, so how do we study melt ponds? A lot of our information comes from these in situ studies. So Shiba in 1998, drifting ice campaign looking at melt pond, looking at different melt pond properties along a 200-meter albedo line, melt pond fraction, melt pond depth. And on the right-hand side, this is a figure from a recent paper by Melinda Webster and others here, but looking at, let's see if I have it. Shiba is in these circles here, and then the mosaic observations are in the squares. You're looking at melt pond fraction versus melt pond depth, and this relationship between fraction and depth observed at Shiba is kind of what was used for a lot of melt pond parameterizations, but clearly that hasn't been consistent across all regions and time periods, as now you can see the mosaic depth evolution with fraction. Depth is increasing and fraction is kind of going all over the place, not really that nice linear relationship that was used to parameterize these models. So kind of thinking more about how these in situ observations are actually representative in time and space across the Arctic. So especially since the Arctic is changing, these two studies were like 22 years apart. So thinking about how we can get more observations of summer sea ice. When thinking about looking at Arctic-wide observations, you naturally go to remote sensing, but remote sensing this summer is kind of problematic because there's a lot of cloud cover in the Arctic. Melt ponds are small in size, so it's hard to resolve from these satellite data sets. There's limited polar coverage, and then also melt ponds look radiometrically similar to open water, both in imagery and in terms of looking at freeboard. It's challenging to calculate freeboard and derived thickness in the summer, and we have these gaps in a lot of our thickness data sets because you can't really distinguish between melt ponds and open water because they look the same. in a lot of remote sensing products, and they also kind of confound these algorithms looking at ice types. So thankfully, there's some new opportunities in remote sensing. Like I said, my work has been using both aircraft and satellite observations, mostly focused on imagery and altimetry. So from satellites, we have WorldView 2, 3, this WorldView constellation that is sub 2 meter pixel size and multispectral, and then Sentinel 2, also multispectral 10 meter pixel size resolution. And then Isa2, photon counting laser altimeter. I'll get into the details of that. And then in terms of aircraft observations, I've looked at a lot of Operation Icebridge data sets. For summer, there's a 2016 and 2017 summer sea ice campaign. 2016 was in the Beaufort and Chukchi Seas, and 2017 was north of Greenland and Ellesmere Island. So a lot of data from these different methods that I've used in this work. Okay, so for Isa2, this was launched in 2018 as a photon counting laser altimeter, which means every individual photon that's returned from the surface is geotagged. Operates at 532 nanometers, so green light that's able to penetrate water, which is important for melt ponds. And then the configuration is that there's 3 beam pairs, and each beam pair consists of a strong beam and a weak beam. The strong beam is about 4 times more powerful than the weak beam, and that's the one that we use in our work. And then there's coverage up to 88 degrees north and south. And then this is kind of showing like what the 1 week of reference ground tracks in the Lincoln Sea look like. But then each of these reference ground tracks has 3 pairs. So yeah, really good data coverage, especially when you get up north. Okay, so this is what the Isa2 data look like. This is the photon cloud associated with one of the lower level products, ATLO3. So each of these are individual photons. And then these observations are obviously in polar day, so you can see some solar background here below and above the surface. You can see strong returns from the surface, some subsurface scattering, likely due to melting surface. And then when you come upon a pond, you can see some nice returns from this pond surface as well as the pond bottom. And so this is really great that you can see these are rather large ponds. These are about hundreds of meters in width and 1 to 2 meters deep. So these are really large ponds, but still really cool. You can see these from space. But the problem with the Isa2 products as they are right now, ATLO7, which is a higher level product that measures the sea ice height aggregating 150 photons at a time, is that it doesn't really consistently track either the surface or the bottom of the pond. It kind of jumps in between or does one or the other, kind of depending on the density of the photons. But regardless, it doesn't track 2 surfaces, so you don't really get any information about the melt pond from this product. So what we're looking to do is kind of develop these algorithms that are able to track both the surface of the pond and the bathymetry of the pond. So we've developed 2 algorithms. The first is the University of Maryland melt pond algorithm, very creatively named, but it requires manual identification of melt ponds. So I looked through a lot of these photon clouds to find melt ponds. But then there's also this density dimension algorithm, and this is part of a family of algorithms developed by Ute Hersfeld and her team that automatically can detect surfaces in these kinds of photon clouds. And this particular algorithm is able to note when there's 2 surfaces and bifurcates. It'll measure the top of the pond and then come back and measure the bottom of the pond. And so in this way, when you difference the 2 surfaces, you're able to derive melt pond depth after correcting for like refraction and stuff. So our study was focused on the multi-year ice region in 2020. So this is the May multi-year ice extent from 2020. We're looking at 2020 because it was the first year of continuous Isa2 data, and also kind of a year of like anomalous melt, really anomalous May temperatures. So these are the locations of the ponds that we've tracked. So the green is showing the DDA tracks. We only ran in about 10% of the data just because it takes a while to run. And then the MPA melt pond, the Maryland one melt pond algorithm, is shown in black. And then the ponds that we've both tracked kind of coincidentally are shown in gold. Right. So when looking at the ponds that we've both tracked, and looking at the average depth from these ponds, there's a good correlation between the depths retrieved from both algorithms, which is kind of a good validation and, good validation and kind of a reason to combine our data sets when we're looking at evolution throughout the summer. Right, on average, the MPA ponds are only like a few centimeters deeper than the DDA ponds. Okay. Also, we looked at Sentinel-2 imagery in the same region, the multi-year ice region, and we've applied this previously developed melt pond or image classification algorithm that takes advantage of red, green, and blue channels, and then the near-infrared channel to classify individual pixels in high-resolution imagery. We've applied this to IceBridge, Sentinel-2, and WorldView data, but kind of starting on the left-hand side, zooming in across the screen, but you can see individual pixels are classified as sea ice, melt pond, open water, or other, and other, in this case, we introduced with these larger pixels because they're kind of mixed pixels at the edges of flows or melt ponds. So we've classified about 1,800 of the Sentinel-2 imagery. So those are 110 kilometers by 110 kilometers. So lots of data there on melt pond fraction and sea ice concentration. With those classified images, yeah, you're able to derive these other parameters that might be of interest to the modeling community. So melt pond fraction is shown in this middle panel here. We have sea ice concentration at the top, and then pond depth from the Isa2 tracking algorithms on the bottom, looking at on the x-axis time. And then we've aggregated the statistics of 5-day running statistics, looking at the median here, and then the interquartile range shown in the box. The background color is the number of observations. So these are number of images in Sentinel-2, and then number of melt ponds observed from Isa2. So going through this, what you're seeing is sea ice concentration starting out high and then kind of decreasing, becoming more variable between the tiles towards the middle of the summer, and then kind of increasing again towards the end. And then melt pond fraction increasing slowly, and then peaking at the end of June, and then kind of decreasing and becoming more variable throughout the summer. Melt pond depth, I should also note that the pulse width of Isa2 kind of restricts being able to separate surfaces that are closer than like 25 centimeters. So we can't resolve ponds that are shallower than 25 centimeters. So this is probably biased high. I know some of you melt pond modelers are probably thinking that, but we have melt pond depth starting off at that limit there, and then kind of increasing. The main statistics here are shown from the combination of the two algorithms. The DDA is shown in green, and that kind of dominates the trend because it observes so many more melt ponds than the MPA. And MPA, like I said, required on manual observations of these ponds. So identifying ponds that were probably the deeper, more obvious ponds rather than the shallow ponds that I wasn't even sure if they were ponds or not. So that's why this one kind of diverges from the rest of the group, because it's really tracking those deep ponds here. But yeah, when thinking about those in situ observations and how melt pond fraction relates to melt pond depth, you don't really see that relationship where as melt pond fraction is increasing, pond depth is increasing. You only see that at the beginning of the summer, but pond depth continues to increase when melt pond fraction decreases in this case. But again, it's hard to compare remote sensing observations with in situ observations because this is kind of integrating a lot of processes over a wide region. Yeah. Right, so in terms of the products that we've created, we did this with the Operation IceBridge imagery. These classification masks are available at on our LSA website, Lab for Satellite Altimetry website, but also long-term archive. So we have these full image classification masks, and then the derived parameters from each individual image, melt pond fraction, sea ice concentration, and then pond color fraction, which is kind of related to the color of the ponds and how the ponds relate to the brightness of the ice in the image. But yeah, we're kind of looking to do the same with the Sentinel-2 imagery. So wrapping up part 1, parts 2 and 3 are much shorter, don't worry. The questions that I have about this and for the modeling community is what can you all use this for? Is this the right kind of format for these data products? I'm hoping that these mass image products would be useful for things like validating melt pond surfaces that were simulated, or under ice light melt pond distribution studies, and help with parameterizations of models, and then what other information would be useful to get from these data sets. And then also looking to how we can validate this work, because these are remote sensing observations. It'd be nice to see some of these really deep ponds and in situ observations, or even aircraft-based observations. And then looking to further apply these algorithms. The image classification algorithm can be applied to other high-resolution imagery. And then the Isa2 melt pond tracking algorithms can be applied to other seasons. And yeah. This past summer, there was, so kind of to follow up on the how do we validate these melt pond depths, this past summer from the 11th to 26th of July, there were these validation campaign based out of Thule. There are 6 science flights, all Isa2 underflights. One of them was cryo to ice, so underflew cryosat as well. It had a high altitude topographic LiDAR, which was near infrared, so that didn't measure melt ponds, but a low altitude green laser bathymetric LiDAR that would be able to penetrate the melt ponds. And the goals of this campaign were to kind of look at how we can improve the Isa2 higher level products and what the Isa2 laser response is to melting sea ice surface, and then also kind of generate an algorithm that can be applied systematically for the melt pond depth recovery from Isa2. Wow, okay, so just moving on to the next part. Now I'm in my postdoc, a postdoc position at Brown with Monica Martinez-Alhamis. And her lab has created this ice flow tracking algorithm that is able to identify flows in MODIS imagery. And then after identifying individual flows, you can extract different features like area, perimeter, minor and major axes. And then looking at consecutive MODIS images, you can track like Lagrangian routes of individual ice flows, and then generate other things like a monthly Eulerian velocity field, and look at dispersion characteristics, rotation, angular velocities. A lot of potential with this algorithm. So what my particular work will be is it's funded by Office of Naval Research, and it'll be looking at flow size distribution transition from spring to summer. And kind of how that relates to the dynamics of the ice, and what features, features kind of relate to how the ice moves and what you can infer about ocean dynamics in terms of, how the ice moves. Okay, so to wrap up, I think that's fine, right? Right, so I'm here as a remote sensing scientist, so I think it's interesting to talk about what kinds of observations are useful for models, how to generate products that can be used. We have these high resolution new observations that are available Arctic-wide or basin-wide scale, which might be, or add information to how we look at melt pond model validation and parameterization. And I think with these different kinds of data sets, from in situ to aircraft to satellite observations, we can look to see how different processes scale, and how we can integrate these data sets to, right. And also thinking about how models can define observational priorities. So when we're looking at different model intercomparison projects, where is the biggest spread in terms of temporally and spatially, from model simulations, where is the most uncertainty in these models? So what observations are needed for the modeling community? Yeah, so with that, I'll take questions.
Well, first of all, thank you, Ellen. There was a problem with your presentation on Zoom. So probably people didn't see them very clearly. They saw them only, it was basically like a camera looking at the screen. So I'm not sure whether you uploaded your presentation on the website. If you could, that would be great. So they, if someone wants to watch it again, then they would have the proper slides. But that's something we can discuss later.
Thank you, Eileen, for your presentation. I would have, it may be too specific, but it was about this flow tracker that you developed. I was wondering if you observed some turbulency into the motion of individual flow, and then if does it is due to a turbulency into the flow of the water, or it's independent to this? I don't know if I make myself clear. I'm just not turbulency. I'm talking about the convection.
No, it's okay. I haven't really started much on this work, but yeah, the idea is to kind of relate the ice movement to ocean and wind, and kind of see that relationship and better like characterize different drag coefficients on either side.
Thanks, Ellen. That was a very interesting talk. You particularly asked, like, what would we find useful, interesting as modelers? I'm a modeler, okay? So, as you know, okay, I'm involved in a project looking at fragmentation of the ice into breaking it up, both mechanically and thermodynamically. And so what I wondered was whether it's possible to look at imagery of melt ponds and before and after fragmentation events, okay? Because it's been shown how the melt pond evolution can fractalize, if you like, and spread out, become interconnected, and then melt the flows along points of weaknesses, and the flows break apart. I'm thinking with the ISAT imagery, you probably have sufficient resolution to see that.
Yeah, so the resolution's not the issue. It's the repeat track is not. I mean, it's a 91-day repeat track orbit, so you're not looking at the same ice. And I think that's kind of an issue for all like satellite observations, that it's challenging to track. You're not doing like Lagrangian tracking of ice. There are studies that have like satellites that track buoys. That, I mean, that could be useful for that.
Okay, so even if you couldn't track a particular event, you would capture snapshots of flows in different stages of fragmenting.
Yeah.
Okay. All right, thank you much.
Yeah. Okay, last question.
I was curious, back to this flow tracker, can you track flows after they've fractured? And do you keep track of those separation events? Yeah,
so there is like individual flow matching between the consecutive images, and I'm not really sure the allowable change of the flows. So if it like fully fractured in half, I'm sure it wouldn't recognize the flow would be the same. But some melting and like fusing of ice flows, I think, is able to be detected. So on a very small level, yes, but not like fully fracturing. No.
Well, thanks everyone. Thanks, Ellen, for your talk and for answering the questions. And I guess we're now off to coffee for about 30 minutes or just under.